Hello and welcome to the next video in this series, which is aiming to help you with your Mathematics for Computing module. In this video, we're going to cover the sets. So we'll go through the set notations and the definitions for sets. Then we look at set operations. Then we go into some details on the Venn diagrams. We'll be covering the laws of set operations, and we'll finish the video with the Cartesian product. So let's look at the notation. In set theory, you probably have come across a few new symbols that you have not seen before. One of those is this funny looking E. This is the symbol to belong to. So you've probably seen something like X belong to N. Basically, that tells me that X, whatever X is, belongs to the set of N. Now that reminds me that I need to talk about some other things. Elements are always small case letters and sets themselves are always capital letters. So that's another rule that we in mathematics use in set theory. Another symbol that has got a specific meaning in set theory is the colon. And the colon you read such that. In a minute, when I show you some definitions, you'll see the exact meaning for this symbol. A couple of more important symbols. One is the curly brackets. So the curly brackets we use to define what is inside the set. So anything that's in between these curly brackets are what belongs to the set. So you can either give a definition here, or you can just list the set elements inside those curly brackets. And the last symbol that I want to talk about is the dot, dot, dot. So the triple dot actually means that you carry on as before until infinity. Right, let's look at some of these in context so you actually know what I'm talking about. So I'm going to give you an example. X belong to N such that 3 less than equal X less than 7. This is something that you might have seen in your lectures or seminars. So these curly brackets here tell me that I am talking about a set. So what's inside here, that's the definition for the set. How I read it: X belong to N such that, and this is the colon here, and this colon separates the definition into two places. Now the first part is always what wider mathematical set I'm choosing my elements from, and after the such that, I'm going to give you a rule which I need to apply to this specific set that I'm defining now. So the specific set is the natural numbers between 3 and 7, including 3 but not including 7. Another example using the triple dot could be just listing the elements. For example, 3, 4, 5, 6 and the triple dot. Now how do I read this? Well, this is basically all the numbers, whole numbers from 3 up. These triple dots means continue the pattern that was laid out in before up until infinity. So in this specific set, I will have all the numbers, all the whole numbers from 3 up. 3, 4, 5, 6, 7, 8, 9, 10 and so on up until positive infinity. So these are the important notations. Now, you have got some very specific number sets that you need to be aware of. So the natural numbers, which we briefly touched on, we use the capital N for it. So capital N is the natural numbers. Now, what do we mean by the natural numbers? Well, the natural numbers are the counting numbers, and these, depending on the definition that your lecturer gave you, may or may not include 0. So these are the positive counting numbers either start with 0 or 1. Please double check that with your lecturer. If it starts with 0, then you start the natural numbers as 0, 1, 2, 3, 4, 5, etc. If it doesn't include 0, then the natural numbers are just 1, 2, 3, 4, 5, etc. Okay, then the next important number set is J, which is the integers. Now in mathematics you use capital Z for this very same set, but for some reason that I don't know, computer science uses J for integers. I suspect that they use Z for something very special, which is different. That's why they're using J for the integers. But what are integers? Well, they are just the whole numbers. So positive whole numbers, which is all the natural numbers, the negative whole numbers like -1, -2, -3, etc., and the 0. So those are your integers. The next set is represented by Q, which is the rational numbers. Now, the rational numbers are the numbers that you can express as fractions, okay? And they are either recurring fractions or finite fractions, such as a half, a third, or 2/7, any number that can be expressed as a fraction. Now, that includes all the natural numbers and all the whole numbers as well, because number 1 can be expressed as 1/1, 2/2, 3/3. So that again can expressed as a fraction of two whole numbers. So the rational numbers are all the positive, negative whole numbers, the positive, negative fractions, and 0. The next set is Q star, which is the irrational numbers. Now, the irrational numbers are the numbers that cannot be expressed as a fraction of two whole numbers. For example, pi. You can't express pi exactly as a fraction of two whole numbers. You can have an approximation to it, but you can't express it exactly. Another example that you might have come across that belongs to this set is E, the Euler number, which value is around 2.71, etc., etc. Or square root of 2. Square root of 2 is also an irrational number. There are no two whole numbers of which fraction you can express square root 2. So there are infinitely many irrational numbers, but you probably did not have much experience with them. And the biggest number set as far as mathematics for computing is concerned is R, which is the real numbers. And the real numbers are all the numbers that we've talked about before. So all the natural numbers, all the integers, all the rational and the irrational numbers put together. Those are all the real numbers. So every number that is on the number line is a real number. And some of those numbers can be expressed as a fraction of two whole numbers, and some of those numbers cannot be expressed as a fraction of two whole numbers, but every single rational and irrational number corresponds to one point on the number line. So what's important for you is to know that these specific capital letters have got specific meanings. So if you talk about N, then you talk about the natural numbers, which are the positive whole numbers. Then J is the integers, which are the positive, negative whole numbers plus the 0. If you talk about the rational numbers, those are always the numbers that can be expressed as a fraction of two whole numbers. You may or may not talk a lot about irrational numbers. You know, those are the pi, e, square root of 2, anything that you can't express as as a fraction of two whole numbers. And the biggest is the real numbers, so they can be positive, negative, wholes, and the irrational numbers like pi and square root of 2. So what is the relationship between these number sets? We can express it in a diagram that leads us to our very first Venn diagram. So the real numbers are the set that contains everything. So as far as mathematics for computing goes, that is your world. You can't have any other numbers, any different numbers than the real numbers. Then out of those numbers, we talked about the rational and irrational numbers. A number is either a rational or an irrational number. There is no such a thing as a number both rational and irrational, simply because you can either express a number as a fraction of two whole numbers, or you can't express it. There is no such thing as you can and can't do at the same time. So the two sets of rational and irrational numbers don't have any common element to them, which means that their Venn diagrams don't have any intersection. So they are two very separate sets. But when we look at the integers and the natural numbers, we know that all the positive integers are the same as the natural numbers. So the natural numbers are fully included in the integers set. And it's the same for the integers and the rational numbers, because every integer can be expressed as a fraction of two whole numbers. For example, -7, you can express it as -7/1. So again, the integers is fully integrated part of the rational numbers. So here is your first Venn diagram and a little bit of more explanation about the relationship between the different number sets. Now we can move on to how we can define sets. Now, defining a set is nothing else just giving clear instructions or some sort of clarification of what belongs to that set. So if I tell you a number or an object, you will be able to decide whether that number or object belongs to the set or not. Now, you've been given two different forms, the enumerate form and the predicate form. Now, we need to sort of learn the difference between the two types of definition. The enumerate form, it has got the numerate, which is the number in there. So basically the enumerate form is listing the elements or giving you the numbers of the set. And the predicate form is giving you a prediction about what belongs to the set. So in the enumerate form, you are listing, you are giving me all the numbers or objects that belong to a set. And in the predicate form, you give me a prediction, you give me a rule as to what belongs to that specific set. So here are some examples, and let's use the enumerate and the predicate forms for the following sets where possible. So set A consists of the positive integers between 7 and 15. So the enumerate form is basically just list all these terms. So what are we talking about? Numbers between 7 and 15. This is why we use mathematical notation, because from the language you might think that 7 and 15 are both included in the set, but actually when you say between these two sets, 7 and 15 themselves are not included in here. If I wanted to be precise and include 7 and 15, then I would say between and including 7 and 15. So which are the positive integers then which are in our sets? Is 8, 9, 10, 11, 12, 13, 14, and again 15 is not there because it's in between the two of them. Now I could have written this slightly shorter. Mathematicians are lazy, so they always come up with shorter ways of writing so they don't have to use as much space, as much ink. So as soon as you establish the pattern, which I can say, okay, 8, 9, 10, from here people see I'm going up in ones, then I can fill in the gap with 3 dots, and then I can just give you the last term. So how would I read this notation? It's 8, 9, 10, and so on up until 14. So follow the same pattern, which is going up in ones, up until 14. So these 3 dots actually contains the 11, 12, and 13. Right, that was the enumerate form. Let's look at the predicate form. So again, A is equal to, now I have to give you what X is from. So X is an integer, so X belongs to J such that, I'm using the colon for that, and now I have to give you where the restriction that gives me the between part. So the X will have to be between 7 and 15, which means I have to put in the inequality signs. And again, I don't put the equal in because I'm not saying including 7 and 15. So let's look at set B. So set B consists of the even natural numbers less than 19. So I'm going to include 0 in my natural numbers, and I need to remember that now I'm only looking at the even numbers. So 0, 2, 4, and I'm again going to use the triple dot, and which is the biggest even natural number that is less than 19? Well, that's 18. And then I can stop here. So that's the enumerate form. And from here, I know that I need to fill in the gaps here with 6, 8, 10, etc., all the way up to 18. So how could I use the predicate form? So set B, now I need to give you some rules. So what do I know about set B? That it consists of the even natural numbers. So X will belong to the natural numbers, and I have got a rule such that X is less than 19 and even. So both of those things have to be true for a number to belong to my set. And look at the last set. So set C consists of the real numbers between -2 and 7. Now, let's just pause here for a moment. What numbers do we have here? Real numbers. Real numbers are all the natural numbers, the whole numbers, the fractions, and the ones that cannot be expressed as a fraction of two whole numbers. So things like pi and square root of 2 would also be here. Now, do I have a chance to list all of these numbers, even just with a pattern? Actually, no, because there are infinitely many numbers in between -2 and 7 that are real. So I cannot write an enumerate form for set C. But I can give you a predicate form for set C. So set C consists of the elements X, which belong to the real numbers, such that X is in between -2 and 7. And there is your predicate form. Again, because we have got infinitely many numbers that this rule is true to, we cannot give an enumerate form. Now that we have a clear understanding on how to define the sets and therefore can decide about an element, an object, or a number, whether it belongs to the set or not, let's do some operations with the sets. Now, you have to learn every one of the following definitions that we're going to mention. I'm not going to go into details because in your lectures you spend quite some time on going through these, but I cannot stress enough that you need to know these specific meanings and definitions, otherwise you will not understand what's going on. So you have to learn what is a subset, what is the difference between a subset and a proper subset, and how can we talk about two sets being equal. And then you need to learn about what do we mean by the union of two or more sets, what do we mean by the intersection of sets, what are a complement of a set, what is a difference of sets, and what is the difference between the difference and a symmetric difference. So again, go back to your lecture notes, make sure that you understand these definitions. You can come up with your own examples that would satisfy every one of these definitions. And on top of that, you also want to be very clear on the symbols that are used for these very specific set operations, so that you don't confuse the subset and the proper subset symbols, or you don't confuse the union and the intersection symbols. These are very, very important, because in mathematics we always use shorthands, we always use symbols instead of having to write too many words. Now, let's look at some examples of how we can use the set operations. So here I have given you some sets, and remember that squiggle is basically the word or your full set that you talk about. So there is no other, as long as this example is concerned, there is no other numbers in my world, just the natural numbers that are less than or equal to 15. So what I would like to start with is actually writing out exactly the numbers that belong to every single one of these sets. So this C, which is my word now, this is my full set, this is the set that contains everything, is the natural numbers that are less than or equal to 15. So these are 0, 1, 2, all the way up to 15, because it's equal to 15. Now then, A is all the even numbers that are in my set, in my full set. So what are the evens? Well, 0, 2, 4, 6, 8, 10, 12, 14, and there's nothing more because the next would be 16, but that is outside of my word. The next set, B, is all the numbers that are less than 6. So those are 0, 1, 2, 3, 4, 5. Because it's less than 6, 6 does not belong to B. And C are the numbers that are divisible by 5 with no remainder. So what numbers are there? Well, 0 can be divided by 5 without remainder, then 5, then 10, and then 15. And these are all the numbers that belong to C, nothing else. Okay, so now first we need to find the elements of A union B, B intersection C, A complement, and then A union B intersection C. And also have to draw the Venn diagrams. So A union B is these two sets unified. So basically all the elements that belong to both of them. So A union B is equal to 0, 1, 2, 3, 4, 5, 6. Then from then on, 8, 10, 12, and 14. And unfortunately, I can't use the triple dot in here because there is not an established pattern. Up until 6, I'm going up in 1s, but after 6, I'm going up in 2s, because these two are very distinct rules I've used for these two sets. So that's A union B. How would I draw the Venn diagram for A union B? So this is A, and this is B, and obviously I would have an intersection because 0, 2, and 4 belong to both of them. So next set that we need to look at is B intersection C. Now what we need to look at is what numbers belong to both of them, B and C. So what are the common numbers in here, B and C? We have got the 0 and we have got the 5, and that's all. Now what is B intersection C? So I'm going to draw B and I'm going to draw C, and the intersection is this part. This is B intersection C. Sometimes you might have seen the union, A union B, drawn like this and then put in these shading lines, so you know exactly that you're talking about all of them. if you want to be exactly clear, just put in the lines. Then we want A complement. Well, A complement are the numbers that is in my word but don't belong to A. So A are the even numbers, so A complement will be the odd numbers. So 1, 3, 5, all the way to 15. Okay, and the drawing now would look something like this. So this is my word. Here is A, and A complement are the numbers or the elements that are outside of A. So this would be the Venn diagram for A complement. So the last set that we need to look at is A union B intersection C. Now for this what we need, and we're going to go back to the previous page for that, is the union of AB, which we looked at here, plus the common elements with C. So this is C, this is A union B. What are the common numbers in here? Well, 0 is a common number, so 0 is one of them. 5 is also in both of them, and so is 10. So these are the common numbers in both of them, and C would have 15, but A union B doesn't have 15. So these are all the terms or the elements in this set. But what does this set look like? So I had the A union B, so this A, this is B, and then I have the intersection of that with C. So here is C. So I need now all the elements that belong to the common part of the union and C. Now this is the union here, this is the union here, and the common parts of that with C is just this bit here. So this is the A union B intersection C, shown on a Venn diagram. Now we can move on to the laws of the set operations, and again I cannot stress enough that you have to learn these laws. Now you might be thinking about, oh no, I have to learn a bunch of laws again, but if you look at them carefully, you will actually recognize that these laws, although look slightly different because they're using a slightly different notation system, they are essentially the same as the laws of logic that you've already learned. So you know in logic what double complement means. You just apply that to the sets. The idempotent law, the commutative, associative, distributive, the identity, annihilation, inverse, absorption, De Morgan laws, you've already learned them, every single one of them. The only difference you need to know now is what is the notation difference, but the meaning you will see is exactly the same. So you can have them in a table format, which your lecturer have already showed you. Again, you need to remember these ones, so compare them with your laws of logic applied to the AND and the OR operations, and you will see that they are basically the same. Let's apply the laws of the sets and prove these two statements. So the universal set intersection A, and then I unite that with intersection B and A, and that should be equal to A. When I look at this expression on the left hand side, what I see is that A is a common term in here, so I can, in mathematical terms, if it was algebra, I could say I can factor A out. But that also means that I'm going to use the inverse of the distribution law So I factor out it with the intersection, and then what's left behind is the universal set union B. So I used, from here to here, I used the inverse of the distributive law. Now, what I know here is that the universal set unified with B, that is my universal set. And that is applied the annihilation law. And then I know that universal set intersection A is actually equal to the set A itself, and that is the identity law. So I showed that this long complicated set expression is nothing else but A. Let's look at the other one, which was the null set unified with A. Then take the intersection of that and the B union A. And we need to prove that this is also equal to A. So again, similarly as here, I'm going to apply the laws of sets to the left-hand side, and hopefully I will end up with the right-hand side. So I can again use the inverse distributive law, but instead of the union, now I apply that to the intersection. So A can be factored out with the union, and what I left with is the null set intersection with B set. Now the null set intersection with any set, that's going to give me the null set, and the null set unified with any set, that's going to give me that set itself. So here I applied the annihilation law, and here I applied the identity law. And again, I manipulated the left hand side, so I ended up with the right hand side, so these two are equal. And that leads me to the last topic I would like to talk about today, and this is the Cartesian product. Now, there is a very important definition here, which again you have to learn. So the mathematical symbol for the Cartesian product is a cross between the two sets. So A cross B is basically the Cartesian product of sets A and B, and that is nothing else but the ordered pairs where the first term comes from the first set and the second term comes from the second set. So let's look at some examples. If I have got set A consisting of the terms 1 and 2, and set B consisting the terms of x, y, and z, then what will be the following Cartesian products? So A Cartesian product B, what will belong to them? Now, from here on, we talk about ordered pairs. It's basically like if you were now, from now on, you were on the coordinate system, you know, the x-axis and the y-axis. So first you always come from the first term, which in the coordinate system would be your x coordinate, and in B would be the second term, which would be your y coordinate in the coordinate system. So the first term comes from A, that can be either 1 or 2, and the second term have to come from B, which is x, y, or z. So combining them all together, I can have 1x, I can have 1y, and I can have 1z. Now I paired up 1 with every possible combination from B, so I can move on to the next term in A, which is my last term, thankfully. And then I have to combine this one now with every single one of the B's. So it's 2x, then 2y, then 2z. And there is nothing else. So I combine everything together. So the Cartesian product AB is consist of the pairs 1x, 1y, 1z, 2x, 2y, 2z. And now one term or one element of this Cartesian product is one of the pairs. So 1x, I treat them together and they are one term, one element of this Cartesian product. Now, what does the Cartesian product AX A look like? Now here I'm choosing both terms from A. So the first term have to be from A, but now the second term also have to be from A. So in this Cartesian product now I will have all the possible pairs of number combinations of 1 and 2. So that can be 1, 1, 1, 2, 2, 1, and 2, 2. And there is no other combinations. I've used up all of the numbers and I placed them in both of the possible places. So the Cartesian product AA consists of 1, 1, 1, 2, 2, 1, 2, 2. Those are the different terms. And the Cartesian product of BB, similar logic, but now applied to the different elements of B, which are X, Y, and Z. So now I'm choosing all the possible number pairs from X, Y, and Z. So it can be XX, XY, XZ. Now I paired up X with every single one of them, so I can now choose Y and pair them up with every single. So YX, YY, then YZ. So I used up Y and paired it up with everything. Now the last will be Z and pairing it up with X, Y, and Z. So the last Cartesian product has got the most elements because that is the biggest combination that I can pick out. Okay, so the important thing here with the Cartesian product that you have to be aware of that the first term always have to come from the first set and the second term always have to come from the second set. Now, if you are using the Cartesian product applied to the same set, then it's somewhat easier because then both of the elements, both of the terms are coming from the same set. So here it's all just the numbers and here it's all just the letters, while if there are two different sets, then you have to make sure that you're choosing the right term from the right set. Now let's look at one last Cartesian product example when we look at triples of sets. So let B consist of A, B, and C, and now we want to find the terms to B cross B cross B. So now we're talking about number letter triples. So we need to come up with some sort of logical way of making sure that we don't repeat and don't leave out any of these triplets. So first, you probably want to come up with all the possible number pairs. And those ones are AA, AB, AC. Then I have got A for the first term, then I switch to B, BA, BB, BC, and then I have got C, so CA, CB, and CC. So these are the doubles, these are the pairs, the Cartesian products. Now I need to make them into triplets. So what I'm going to do now, I'm just going to place A in front of every single one of them, then B in front of every single one of them, and then C in front of every single one of them, and that means that I've got all the triplets. Unfortunately, there is no shorter way of doing this, so please bear with me while I'm copying them all out. So A, then I've got A, B, and I've got A, C, C. This is one lot. Then I've got B, A, Now I've got B, A, B, and then I have got B, C, C. And I'm going to leave you to do the last one, and basically all you need to do now is just put C in front of every one of these number pairs, and then you have got the last row of all the triplets, and then you end up with everything that you needed. Well, thank you for your attention. I hope that this video helped you to understand a little bit more about sets, and see you in the next video.